Last class we discussed about equivalent DFAs and also the concept of minimal state DFA for any regular language. Today we are going to discuss an algorithm for obtaining the unique minimal DFA for a regular language. So, the algorithm is for minimizing the states of a given DFA. From the previous lecture, we saw that these two are equivalent DFA, and if you are given this and want to obtain this, you need to find these two states as equivalent and needs to collapse them into a single state. This was the second example where if you want to obtain the minimal state DFA, you want to first find Q2, Q4 as equivalent and collapse them, then you find Q1, Q3 as equivalent and collapse them into a single state. This is the third example that we discussed. Here you have to find these three as equivalent and needs to collapse them into a single state. So, we need to find how two states can be equivalent, and if you are finding two states are equivalent, how can you collapse them into a single state? So, these are the two questions that we want to answer, and in order to answer the first question, we will be answering the opposite question. So, how we can find states which are non-equivalent? Suppose you are looking at a pair of state PQ, either they are equivalent or they are non-equivalent. So, if you can answer whether they are non-equivalent, it will give you an answer to this question as well. And today we are going to see a technique for answering this question, whether two states are non-equivalent or when you want to keep two states in the automaton, you are not allowed to collapse them. So, we can ask this question, how we can find states which are non-equivalent. So, we are asking here, are the states P and Q equivalent? Suppose they are equivalent. Suppose we say that they are equivalent, then what we do? We will be merging them into a single state PQ. So, naturally the resulting automaton will look like this. Then is the automaton B equivalent to A? See the language accepted from the figure. From the figure, X is not in the language of this automaton because it ends in a non-final state, and Y is in the language. But if you look at this automaton, both X and Y are in the language. So, definitely A and B are non-equivalent because of X not in the language of A and but is in the language of B. This is because we merged and made the merged state a final state. Now, maybe you can try the other possibility of making PQ a non-final state. Then what is the case? Both X and Y are not in the language. So, here Y is going to distinguish, because Y is in the language of A and not in the language of B, they are non-equivalent. So, what we observe from this example is that two reachable states P and Q, a pair of state PQ, is non-equivalent when one of them is non-final and the other one is final. It does not matter which one is final. If one of them is final and the other one is non-final, then they cannot be equivalent, because if you decide them as equivalent and merge, you will get get a DFA which is not equivalent to the given DFA. So, you cannot merge them. So, we found that when we are looking at a pair of reachable state where one is final and the other one is non-final, they are non-equivalent. Now, we need to find an answer when two reachable states both are non-final. Are they equivalent? See this situation, x is taking you from the start state to P and y is taking you from the start state to Q. So, they are reachable, but both are non-final. So, you cannot apply the previous technique, but you are looking at a string Z and the path for Z from both this P and Q. One of them is going to a final state and the other to a non-final state. Now, suppose you look at this machine, you can see that x z is in the language and y z is not in the language. And now, suppose the string z is a sequence of n letters a1, a2, etc. an. So, this is actually the path a1, then a2, a3, likewise it goes. The same sequence of letters here as well. Now, suppose you say these are equivalent, then what you do? You will merge them into a state PQ. Now, you look at this machine, you can see that it is not a DFA because from the single state PQ, the transition for the same simple A1 is going to both the state P1 and Q1. So, two transitions are there for A1. So, this is not a DFA. To make it a DFA, there is no other way than merging P1 Q1 into a single state. This is the only way. So, as a consequential impact of merging P and Q, you have to merge P1 Q1 into a single state. Then the problem is getting transferred to here. Now, A2 is having two transitions from P1 Q1 and this will continue until you merge all the subsequent pairs of state until you reach into RT. So, this is what you will obtain if you decide to merge PQ or decide PQ as equivalent. Now, see, this is the path. Now, we are asking this question, is A and B equivalent? And not that XZ is not in the language and YZ is not in the language, because you assume that RT is made a non-final state, then both are not in the language. But here XZ is in the language, so they are non-equivalent. Now, you consider the other possibility where the state RT is made a final state, then in the resulting machine B, both XZ and YZ are in the language, which is different than this because here YZ was not in the language. So, in this case as well, A and B are non-equivalent. So, what we are learning is that two reachable states P and Q both can be non-final or final. For the final case as well, the situation is very similar. So, we are here looking at two reachable states, both are non-final or both are final. They are not equivalent if there exists a string Z for which path from one of them going to a non-final state and the path for the same string from the other going to a final state. So, we wanted to answer this question, and to answer this question we have these two answers. If you are looking at a reachable pair of states, one of them final and the other one non-final, then they cannot be equivalent. And if you are looking at a reachable pair of final or non-final states, then they are not equivalent if there exists a string for which the path from one of them going to a final state and the path from the other going to a non-final state. And we can actually combine A and B into a single statement like this. two reachable states P and Q, regardless of whether they are final or non-final, if they are reachable, they are not equivalent if there exists a string Z for which the path from one of them going to a final state and path from the other going to a non-final state. You may wonder why these two are combined. We just avoid having A and we just remove this condition, both final or both non-final. Then the question is, how is it that A is addressed? I can tell you, this is actually A when one is final and the other one is non-final. In that case, you take the string Z as epsilon. You can see that the path for epsilon from P ends in P, which is a final state, and the path for epsilon from Q ends in Q itself, which is not a final state. So, you have an Z such that path from one of them for Z going to a final state and from the other going to a non-final state. So, Z is epsilon for the first case. So, the second ln is enough by removing this restriction. I hope you are with me. This is what I said, epsilon is a string witnessing the non-equivalence for P and Q in this case. So, two reachable states P and Q are not equivalent or non-collapsible when there exists a distinguishing string Z such that the path for Z from one of them going to a final state and from the other going to a non-final state. So, if the states P and Q are non-equivalent, then there exists a string Z witnessing the non-equivalence of P and Q. That is what we said. And if you have such an Z, you can prove that then there exists such an Z of maximum length, the number of states in the DFA, because this is the string that you are looking at and the length of the maximum length of a path without a cycle is bounded by the number of states in the DFA. So, you can say that if there exists such a path, then the shortest one will be having length less than the number of states. So, this is true. It follows from the fact that n minus 1 is the maximum length of an acyclic path. So, if this path is acyclic, then the maximum length is n only or n minus 1. And if it is cycle, no need to retain the cycle, just cut away the cycle and you will get a string. So, this actually allows us to get an algorithm to decide whether a pair of state is not equivalent or not. You will either get epsilon as the string distinguishing them, or you will get a string of at most size n, where n is the number of states in the DFA for distinguishing P and Q. So, you try for all these strings up to length n, and if you can find a string distinguishing them, you made them non-equivalent, and if you cannot find such a string of maximum length n, then that means they are equivalent. Okay. Now, we can look at the algorithm. To mark a pair of states PQ as non-equivalent, the algorithm needs to find a string Z witnessing the non-equivalence of P and Q. So, this is the algorithm. Let us see what this algorithm is going to do. It marks a pair of state PQ as non-equivalent if one of them is final and the other one is non-final. That is, it see whether epsilon is a string distinguishing them, that is a string of length 0. If yes, you mark them. So, epsilon is the string which allows you to do that. Now, we do not read this sentence, I will tell you what you can do. Suppose you have a pair of state PQ not marked as non-equivalent, they are not marked as non-equivalent, and suppose that for the simple A from P and Q you are reaching into a pair of states RS, that is delta P comma A is R, delta Q comma A is S. Suppose you are reaching into a pair RS which is marked then it says you mark PQ also as a pair of non-equivalent state. Why? Because you are assuming that RS is marked, then by definition, why is it marked? Because you can find a string Z such that the path for Z from one of them going to a non-final state and the path for Z from the other is going to a final state. And that is why you said R and S are non-equivalent. See, we are looking at non-equivalent states, not the opposite. Then you can easily see that, okay, for the same reason AZ is going to be the string distinguishing P and Q. That is what I am telling here. So AZ is taking you to a final state from P and AZ is taking you to a non-final state from U, and hence AZ is that string which distinguishes P and Q as non-equivalent. So you can say that if PQ is non-equivalent, sorry, it is not marked as non-equivalent, but from PQ you are reaching into a pair of state marked as non-equivalent, then you mark PQ as well. Okay, now I hope you got it. We can try to apply this algorithm. So in the algorithm you are basically trying to mark pairs of states in this table. These are the pairs of 36 pairs of states in this. So if you look at the first step in the algorithm, it says mark a pair if one of them is final and the other one is non-final. So you will get all these marked. If you want, you can verify. Why is it that Q4 Q1 is marked? Because Q1 is final and Q4 is non-final. Maybe you look at this as well. Why Q1 Q2 is marked? Because Q1 is final and Q2 is non-final. So every such pair is marked by the first step. So after the step 1 you are getting all these markings. So wherever there is a mark you cannot merge them. For example, Q1 and Q2 cannot be merged. Q1 and Q2 cannot be merged because one of them is final and the other one is non-final. Note that we are marking non-equivalent states. Now the second step. It tells you that if you have a pair of states, say maybe here, not marked, but you can mark it using the second step. Maybe we can verify it. Why is it that Q3 Q5 is marked? Because you can see that Q2 Q5 is marked and you apply this, you substitute PQ as Q2 Q5. Okay. If Q2 Q3 Q5 is not marked, was not marked before, see that it was not marked, this was not marked, Q3 Q5 was not marked, and from Q3 Q5 if you apply A, from Q3 on an A you are getting into Q2, Q3 on an A you are getting into Q2, from Q5 on an A, Q5 on an A you are getting back to Q5. So you found that Q3 Q5 this one was not marked, but from that pair on an A you are reaching into Q2 Q5 which is already marked as non-equivalent. Then by step 2 you are marking Q3 Q5 as well. That is what you did. So after applying the step 2 once in the loop you will get this state. Other red markings you can similarly verify. Now you try to apply the second step again, you can see that you are now in this second execution of the same statement you are making some blue marking. Maybe we can try verifying one. Why is it that Q0 Q2 is marked? Because you note that Q1 Q5 is marked in the previous step, and from Q0 Q2 on A, from Q0 on A you are going to Q1, Q0 on A to Q1, and from Q2 on A you are going to Q5. So, from Q0 Q2 on A you are going to Q1 Q5 which is already marked, and hence you are marking Q0 Q2 as well by applying the second step. You can verify how the other blue markings are done. You do it offline. Now you try applying this step again. You have to apply this for maximum 6 steps, because 6 is the maximum length, or 5 steps, 5 is the maximum length. But here you cannot find any more markings, no additional marks can be made. So, you can stop actually, because even if you go for the next step, nothing will happen because you cannot mark any more pairs. So, the moment you get into such a state where no markings can be made, you can stop. And not that this matrix is symmetric, because here if you mark Q0 Q1, then Q1 Q0 can be marked. So, only one triangular portion needs to be filled by the algorithm, then you can automatically fill the other portion. So, this is what we said. Two pairs, a pair of states P and Q which are reachable are marked as non-equivalent or non-collapsible when there exists a distinguishing string Z, making them non-equivalent. When I say distinguishing string, I mean the path for the string from one state going to final state and from the other state going to a non-final state. And if a pair of states PQ is left unmarked as non-equivalent, if you look at this state, if you want to see this pair Q3 Q1 or Q1 Q3, it is left as unmarked. If a pair is left unmarked as non-equivalent, when this algorithm finishes execution, then they must be equivalent. For example, all these pairs are equivalent because there is no string distinguishing them. And these are the equivalent pairs of states. And if you look at this set of pairs as a relation, you can verify that it is an equivalence relation. What is an equivalence relation? It is reflexive. You see that, see Q0 Q0, Q1 Q1, Q2 Q2, Q3 Q3, Q4 Q4, Q5 Q5. So, the reflexive pairs are there. So, it is a reflexive relation, all the pairs are there. It is also symmetric. Verify that Q1 Q3 is there, then Q3 Q1 is there. Q2 Q4 is the other pair for which we have Q4 Q2. So, it is symmetric. So, we are verifying it for this particular instance, right. It is transitive. There are many pairs Q1 Q1, Q1 Q3. It needs to have Q1 Q3 which is already there. Next pairs Q1 Q3 and Q3 Q1 demands you to have Q1 Q1 which is already here. Then the next set of pairs Q1 Q3, Q3 Q3 demands you to have Q1 Q3 which is already here. Next set Q2 Q2, Q2 Q4 demands you to have Q2 Q4 which is already here. Now Q2 Q4, Q4 Q2 demands you to have Q2 Q2 which is there. Next pair set of pairs is Q2 Q4 and Q4 Q4 demands you to have Q2 Q4 which is already here. That we verified that the relation is reflexive, symmetric and transitive. That is, whenever we find that two are equivalent, that is an equivalence relation. Now you see that these are equivalent state Q0 Q0, Q1 Q1, Q2 Q2, Q3 Q3, Q4 Q4, Q5 Q5, of course because they are the same state, and for merging nothing to be done, they are only single states Q0 and Q0, Q1 and Q1, nothing to be done. So, that part is over. Now, if you look at these two pairs, it is Q2 Q4 and Q4 Q2, the same set of pairs. So, you want to collapse them into a single state. What you do? You merge them into a single state and redirect all these arrows to that state. That is what I did. And outgoing arrows you are taking from the same merged state. Now, the remaining pair is these two pairs Q1 Q3 and Q3 Q1. So, they are the same set of pairs, you merge them together. So, we are done. The states of the resulting machine B is actually the equivalence classes of this equivalence relation. That is what we are observing from this example, which we can formalize now. This is the relation that we looked at. Now, we are just looking at when they are equivalent. That means, you cannot find a string Z such that Z can distinguish P and Q, or in other words, when they are equivalent for all the string Z, the path for Z from P is going to a final state if and only if path for Z from Q is going to a final state. So, you cannot find an Z such that for the string Z, one of the path ends up in a final state and the other one is not in a final state. That you cannot have. If you have such a path, then P and Q are non-equivalent, but here we are looking at the equivalent states. That is, for all strings Z, the path for Z from both P and Q will go to final states, or both will go to non-final states. That is it. And you can easily verify that this relation, that is the equivalence relation which makes two states equivalent, or the algorithm left us not marked, that relation if you look at, you can easily verify that. You do it offline, you can verify that the relation we defined here is reflexive, symmetric and transitive. Now, the minimal DFA B from the given AFA A can be obtained directly from the relation, this equivalence relation on the state set of A, and this algorithm is what is called the quotient construction, and the equivalence classes of this equivalence relation. In the previous example, 4 equivalence classes we obtained, and they are going to form the state set of the required DFA. Then the question is, which equivalence class is representing the initial state? The equivalence class where the start state of the given DFA present is the initial state of the required DFA. Then which are the transitions? We are going to see from the equivalence class for P on an A where you are going. You can easily verify that you are going to an equivalence class for the state to which you will reach on A from the state P in the given DFA. That is how it is defined. You can verify it offline. And the set of final states of B is the equivalence classes corresponding to the final states in the given DFA. So, here what we discussed is that you can have this equivalence relation on the state set of the given DFA, and that equivalence relation is going to give you the required DFA directly, where the equivalence classes of that relation is going to become the states of the DFA. If you recall, in the previous example, 4 equivalence classes we obtained, and correspondingly we obtained 4 states. And the equivalence class for the start state of the given DFA is going to become the initial state of the required DFA, and the equivalence classes corresponding to the final states in the original DFA is going to become the final states of the required DFA, and the transitions are defined like this. With this, we are coming to the last part of the lecture, where I am giving you two exercise questions here and here for you to practice and understand how the algorithm can be applied to obtain a unique minimal DFA. And after you obtain, you also observe that the minimal DFA, the states in the minimal DFA is the equivalence classes of the relation that we defined in this slide. Today we have seen an algorithm for finding the minimal state automaton from a given deterministic finite state automata. Thank you.